Hi, my name is Levi Lelis and I'm an assistant professor at the University of Alberta. I'm also a professor on leave from Universidade Federal de Viçosa in Brazil. In this paper, I presented a unifying perspective for a family of algorithms for solving planning problems for zero-sum games with exponential action spaces. In this paper, I showed that a very simple variation of a known algorithm, NaïveMCTS, can be used to describe a family of algorithms that were invented by different research groups for solving planning problems in exponential action spaces. And I'm going to briefly go through some of these algorithms, and you're going to see at the bottom of the slides the citations. And then this algorithm that we have, this unifying perspective, it's able to describe all the algorithms mentioned in this talk. Let's say that we want to control a set of components, which could be units in a real-time strategy game. All these units, they can issue different actions, and if you want to control them, then you have to choose an action for each one of these components. The number of different actions that we can take, different combinations of actions that we can take, it's going to be exponential. So if you have a different actions for each of these components, and we have n different components, then we're going to have a total of a to the n different combinations of actions that we could take. So this is a very challenging problem from the planning perspective because of this exponential action spaces. So one key idea that we've seen in the literature is to use what we call uniform action abstractions, which is just a way of encoding domain knowledge to throw away some of the actions available to each one of the components so that we can reduce the action space. And we've seen many different search algorithms being presented throughout the years that do use this idea of uniform action abstractions. A follow-up work is the idea of using asymmetric action abstractions. Like for instance, we could have components that are more important than the other components, and maybe they deserve to have a finer plan being derived for them. Like for instance, we have these two components here at the top, and maybe they're more important than the others. Like maybe they're controlling the arms of a robot, and the robot is trying to open a door, and all the other components are controlling the wheels of the robot. Assuming that the robot is already placed in front of the door, then we don't have to worry too much in planning the wheels, but what the wheels are going to do. But we could spend more could try to find a finer plan to decide on the actions of the robotic arm. So for these two components, we're going to use all actions available. Another idea is to use what we call a stratification of the components. Like we could divide all the components into different groups, and instead of looking for specific actions for each one of the components, we're going to look for actions for a group of components. So then maybe the group on the left, all components, they're going to move forward, and the group at the top, all components are going to move down, and the group at the bottom, they're all going to move right. So then as we search for a single action for a group of components, then we're also able to reduce the action space. And what I'm going to do now, I'm going to explain an algorithm called portfolio greedy search that uses a uniform action abstraction. Portfolio greedy search was invented by Dave Churchill and Michael Burrow in the context of real-time strategy games. So all the components that we're trying to control here, they're going to be called units, which are the units that we control in real-time strategy games. Once I explain portfolio greedy search, I'll then explain NaïveMCTS, which is the algorithm that's going to enable us to create this very general unifying perspective that's able to describe all the algorithms mentioned so far in this talk. And then I'll show how this variation of NaïveMCTS can be used to implement portfolio greedy search. And let's say that we have three different units, U1, U2, and U3. And the way that we're going to encode domain knowledge to create this abstraction is through what we call a portfolio that we see here on the left-hand side. And this portfolio is composed of two different strategies, S1 and S2. S1, for instance, could always say move to the left, and S2 maybe it's always is going to say move to the right. So it's some domain knowledge that's encoded in these two strategies, S1 and S2. And instead of accounting for all possible actions for these three units, we're only going to count for the actions returned by one of these strategies that we have in our portfolio. So we're going to get started by seeding this units. Let's say that all units are going to follow the action that's returned by strategy 1, S1, and we evaluate it. Let's say that we receive this value of -10, which is not looking good for our player. Now we try with all units playing accordingly to strategy 2, S2, and let's say that we evaluate it again and we see this +10. So +10 is looking better, so we're going to fix all these units with this +10. And then what we're going to do next is we're going to perform a hill climbing search, where we're going to try to change the strategy that's attributed to each one of these units one at a time to see how much we can improve in this value that's being attributed to the units. So we get started here with the first unit, and then we try all the possibilities. We tried already S2, so then we try S1. Our evaluation function says it's +15, so it's already looking better. So we're going to keep this configuration for the units for now. Then we move to the second unit, and then we try another combination. Well, now we replace S2 by S1, and we evaluate it. We see -15, so this is not looking good for our player. So we roll back and we keep the S2. And then we move to the last unit, and then we try S1, and then we see this value of +20, which is the best value that we've seen so far, and that's going to be the actions that we're going to return for all these units. So as you can see, in addition to reducing the action space by using this portfolio that gives us this uniform action abstraction, we're also doing this hill climbing search, and we're not looking for all possible combinations that we have here. We're going to follow this greedy search in order to try to find a solution to this problem. Another search algorithm, and this one is the entry point for this unifying perspective, is combinatorial multi-arm bandits, and we're going to combine those with Monte Carlo tree search. So we have a small pseudocode here on the left hand side, and here on the right hand side we have a state of the game. Let's say this is a real-time strategy game where we have 3 units, and the way that this NaïveMCTS, so that's the name of the algorithm, works is as follows. We're going to have a policy which is called pi0 we have here at the top, and this policy is going to decide that we either going to explore or exploit. And let's say that in the first step we choose to explore, and if that's the case, then we're going to use another policy which is our pi-l, and the pi-l is going to go through each one of the units that we have in the state here at the top, and we're going to choose a action for each one of these components or units. So we go through U1, U2, and U3, and then let's say that U1 is going to move to the left, U2 is going to move down, and U3 is going to move to the left. So we're exploring the action space. And then we create this vector here, and this vector is known as a macro arm. So then we evaluate this macro arm that we just created with pi-l, and then we receive this +20. This value is going to be used by pi-l to form other macro arms, and the details can be seen in the paper. But then we go for another iteration of the algorithm, and now let's say that we again decide to explore, so we're going to create a new macro arm. Again, we invoke pi-l, and pi-l is going to return us another macro arm, which is one action for each one of these components, and this is leading us to a different state. That's what these circles are representing here at the bottom. And then we go for another iteration, and now we decide to exploit. And now we decided to exploit, so it gets to choose one of the macro arms that you already have appended to this tree that we're building here, and it decides to pick the one on the left hand side. And once it does it, then what we're going to do is we apply the same strategy now at this new state that we have here at the bottom. So now we're going to apply what we have here on the left hand side on this state, and then we get to choose whether we're going to explore or we're going to exploit. Because it's the first time that we're seeing this state right here, then naturally we have to explore. And that means that we're going to find a macro arm for the components that we have at this state, which is going to lead us to a new state. And again, we're using pi L to make this decision. So as you can see, we're building this tree like in a very similar way that how we have with Monte Carlo tree search algorithms. The difference is that we decide where to go in the tree based on this algorithm that we have here on the left hand side, which is called Naïve sampling. That comes from the Naïve name that we have at the top. This algorithm, it's actually pretty general, and I'm sure that Santi Ontaillon already had in mind this family of the algorithms when he invented NaïveMCTS, because once you define all these policies that we used in the previous slide, then you have a different algorithm once you define a different policy. And here we're going to take a step further, and in addition to defining all these policies that we have for NaïveMCTS, we're going to make it a little bit more general by defining other components, like for instance how to serialize different strategies in case you have simultaneous move games, or how you use the evaluation function, how to use an opponent model, which is something that it's not used in NaïveMCTS, but it is used in some of the algorithms that we mentioned before, for instance in portfolio greedy search, and even how to return the best action encountered during search. If we expose all these different components, that we can make this super general. And that's the idea of GEX, this general combinatorial search for exponential action spaces, which is NaïveMCTS, but we're gonna expose and make it more general all these other components that we see here in this slide. And once we do that, then we're able to describe all the algorithms that we mentioned in this talk so far, and some other algorithms that I didn't have time to mention. So just to give you a little bit of a flavor of how this can be done, let me show how to implement portfolio greedy search, the algorithm I described, the first algorithm that I described, and this framework. So the idea is that we're going to use a deterministic evaluation function, as is done with portfolio greedy search. And we're also going to limit the size of the tree. So I have this tree here on the right hand side to represent this, but we're going to limit the depth of the tree to be equals 1. So we have the root, and we get to see the children of the root, and nothing more. And once we do this, because we have this deterministic evaluation function and we're limiting the depth of the search tree, then pi 0, it's always going to explore, because it doesn't make sense to exploit, because once you evaluate it once, each one of these macro arms, you don't need to evaluate them again. So you're always going to explore, you're always going to add new macro arms to this level of the search tree. This pi L policy is going to follow a deterministic procedure, which is going to mimic the greedy approach that I showed in the search for portfolio greedy search. So the way that we're going to choose each one of the actions while forming these macro arms, it's going to mimic the hill climbing approach that we did with portfolio greedy search. Moreover, whenever we're creating these macro arms, we can only choose from actions that we have in our action abstraction. Just like in the way that we define an action abstraction with the portfolio for portfolio greedy search, here we only get to choose the component actions which are related to our portfolio. There's some more bookkeeping that needs to be done, but we can actually get the exact implementation of portfolio greedy search with this GEX algorithm. So maybe this looks like a silly exercise because we're making it more complicated, right? If I can describe portfolio greedy search the way it is, then it's easier to describe it that way than using GEX to then describe portfolio greedy search. But the interesting part here is that once you start thinking about GEX, we can get bits and pieces of different existing algorithms and then assemble a new novel algorithm that was never tested before. For instance, we could use stratification with NaïveMCTS. There's also another algorithm that can be described by GEX that I didn't mention in the talk, which is nested greedy search, which could also be used to do the opponent modeling for NaïveMCTS. We could also see that this pi L policy for defining the macro arms, it's just a local search algorithm. Like for instance, portfolio greedy search uses hill climbing. There's another algorithm that's called portfolio online evolution that uses a genetic algorithm. So now we can change this policy pi-L by a different local search algorithm, and that's going to result in a different algorithm for planning in exponential action spaces that we haven't tried before. And these are all very interesting research directions to be investigated. So if you're interested in doing research in this area, then I recommend that you take a look at this paper and see a novel algorithm wasn't implemented yet within this framework, and that might be a good way of starting doing research and planning for these exponential action spaces. Thanks for watching the video, and let me know if you have any questions.